Yeah, starting the recording and welcome everyone. Welcome to RFCs We Love, IoT edition. Thanks for being here on a Friday. Uh, this is our 19th meetup and the sixth continuous since we went on a lockdown. So, we have been consistent, much more consistent in this COVID world than before, where we have been doing this for 3 months, but now we have been doing it every month. So, this is pretty good. If this is your first RFCs We Love, this has been organized by IIESOC, which is India Internet Engineering Society. We organize these meetups as well as organize an annual pre-IETF forum called Connections. I'll talk about that in one of the slides as well. So before we start, head to your Zoom client, click on the poll. We wanted to see like what's the makeup of people who are attending, how many people have been attending this regularly, and how many people this is the first meeting. So this would be a good idea for us to know what's the makeup of the room. So I'll give you a minute. So lots of coming in, lots of people. This is the first meeting, so welcome. It's always good to see new folks coming in, and we are reaching new crowd. Excellent. So I'll leave the poll open for a while, and there are still a few of you who have not voted yet. But it's a good idea that we have a couple of old timers and a lot more new timers. So I will try to explain who we are in next couple of slides as well. So just something that we usually do, we bring in the use from IETF. Not everybody here is a regular IETF participant, but this is a good opportunity for us to provide you what's happening and what you need to be aware of regarding the IETF meeting. So the next IETF meeting is IETF 109. It's from 16th to 20th November, and it's actually in the best time for us in India. It starts at 10:30 a.m. and ends at 4:30 p.m. For us in India. So this is the like actually as feels like optimized for us. So take this opportunity. Like usually it's we are attending in in late nights, but this time it is optimized for us. The agenda is already published, so get to know when your working group is happening. Apart from the regular working groups and research groups, the hackathon starts on November 9th. So this is again a week-long event. So if you are interested in hackathon, you need to register that for that separately. Look at the projects that are happening. So now would be a good time to get involved with the hackathon planning as well. There is an event called IEPG, which happens on Sunday. For the last couple of meetings, it was not happening. This time it's going to happen on a Sunday. The schedule will be out soon. So this will be on November 15th. If you care about BGP operations and DNS, this is the event to attend. So pretty good conversations that happen in IEPG, which is actually outside of ITF. Then the new BOFs or the new working groups which are going to get discussed is APN and MADINAS. APN is application aware networking. So they will be talking. There was discussion about this even in the last ITF with network tokens. Now they have an APN, so two different proposals are in the air for this. So it will be a good discussion. The MADINAS is MAC address identifier in network and application. Again, something new, bit controversial. Let's see how these go. So these are some new conversations. We'll just be starting. So it will be a pretty good session to join in ITF, apart from your regular working group session. There is a fee waiver program. So if IETF fees is a barrier for your participation, please apply. And it's no question asked. So please feel free to use this opportunity to attend ITF. If you are an ITF regular, the NOMCOM is asking for feedback. And if you care, please do provide feedback for your ITF chair, your ADs, your LLC. If you have issues with how these remote meetings are happening and want to give feedback of whatever that's concerned to you about ITF, this is your opportunity to provide feedback. So just you need a data tracker account and go to the NOMCOM website, which I've put. I'll be sharing this slides anyway, so all these links would be available to you to use. The final thing, I saw that some of you are new here, and it might be possible that ITF would be new for you as well. Before the last ITF, we did RFCs We Love focused on uh, what to do on your first ITF meeting. So this is the link from the July RFCs We Love, where we had an intro to ITF, tips to attend your first ITF meeting, what we have been doing in India, for instance. All that information is available there. So you have very good information for you if this is your first ITF meeting that you would like to attend. And we are available at any time. If you have any questions, we would be able to answer those questions for you. Use the question Q&A feature if you have any questions regarding anything, and use the chat feature if you want to just chat among the attendees. Okay, apart from ITF, what's the news from our side? Uh, we have two news for you. There is a project called IPv6 Deployment in Enterprises, which is a grant that we have got from ASIF Asia, which is funded by APNIC Foundation. And if you are interested in IPv6 deployment, please do register at our website, iisoc.in/IPv6, and we will get in touch with you about the webinar schedule as well as case studies of doing IPv6 deployment at enterprises. So this is a good opportunity for you to uh, take part in something concrete that we are doing. And if IPv6 is of interest to you, please do join. And as I said, we do an annual event called Connections. This time, instead of it being pre ITF, we are doing it post ITF, and we are doing it in collaboration with a US India joint event with INTC as well. And some of you would have been seeing emails from Nandini about the various things that INTC webinars, for instance, that they have been doing. So it's pretty good to collaborate and come up with a common event. Since it is a US India joint event, the time zones are a little difficult to figure out, but this is the best that we are able to do. Uh, it's a week long event. Each day it will be just 2 hours or 2.5 hours, 2.5 hours maximum. So it won't be a very long event, but we will do it for 5 days. Monday and Friday, we will start late at 8:30 p.m. in India. And Tuesday, Wednesday, Thursday, we will start early at 8 a.m. in India. We would have a awesome keynote panel with internet pioneers. Some of them have already confirmed. More information is coming out soon. We have tracks on IPv6, on transport, things like Quick, and other things that are happening in ITF. We have a good tutorial for you for 5G for an IP guy. We are doing things like what's hot in networking. In fact, things like APN would be discussed in this track as well. So pretty interesting set of tracks and talks that we have planned for you in the month of December, and more details will be coming out on our website soon. So hope you are excited as we are. Okay, final ask. Since some of you are new, stay connected with us. We have a mailing list hosted in one of the ITF mailing list. I'll put the links in the chat after I'm done. We have a direct email, Twitter, WhatsApp, whichever way you would like to connect with us. There's a whole community here. Use this and ask questions and just network. Okay, I'll give off now to Praneeth, who will start the program, introduce the speakers, and have a really good session today. Thanks. Off to you, Praneeth.
Yes, hello everyone. As we've already mentioned, this is our IoT edition of RFCs We Love. And today we have two speakers, Brendan and Thiru, who will be talking about some interesting stuff in IoT. Next slide, please. Brendan is basically an engineer with ARM, and he's a very experienced developer since a long time. And he has held different roles from hardware design through software security. In his current role as a software architect for firmware update in ARM IoT platform, Brendan has been improving the state of firmware update both at ARM and through the standard organizations such as IETF. And he has also taken a role in ARM and the research security group, where he continues to drive the IoT device security forward. Today, Brendan will be talking about the software updates for IoT, which is the suit working group. And it is indeed an honor to have Brendan with us today. So, welcome to ISOC, Brendan, and we can't wait to hear your talk. Next, we have
Let's start with the Brendan's talk, and then we'll come back to introduce Thiru.
sure. Please, Brendan, take over.
All right, just one moment. Here we are. Have you got my screen?
Yes, we can do that.
Excellent. Okay. Right, let's get started. So I'd like to talk about a few things. First, why I joined the IETF, and my own first experiences in the IETF. It wasn't that long ago, and advice for getting started if it's new to you. I want to talk about how the IETF shaped my work, because I think it's had a really dramatic effect in how I have progressed with the work that I've been doing. And then I'll talk about an introduction to firmware updates and to the suit manifests in specific. So why I joined the IETF? Well, at the time that I joined, I was working in ARM's Embed Cloud firmware update team. Later, that was renamed to Pelion. And we had gone through a pretty extensive design process to build up a firmware update manifest format. We'd originally planned to do this in CBOR, but later changed to ASN1 due to the fact that certificates use ASN1 encoding. Now, this doesn't sound very interesting right now, but it'll be funny later. We wanted interoperability, and we wanted that for a few reasons. I mean, we were building a cloud service, and we wanted to reach the widest range of devices we could. So that meant that we needed a standard that anyone could implement, because that way that anyone would be able to use our services. There are a few other advantages to standardizing, but I'll come back to that in a minute. So we didn't see a standard that we thought would be usable for what we wanted to do. And so we sort of looked around at what standards there were out there, and most of them weren't really appropriate for deeply embedded devices. So we saw that there was a need there, and we thought that that would be a good approach. So when I went to my first IETF meeting, it really didn't go how I expected. Now, I've got some advice if you're going to attend your first IETF meeting. This advice is probably not that helpful in the world of full virtual meetings, but when we get back to in-person events, I would suggest that you go to the whole event. I had a single day pass, and I missed out. So I missed all of the newcomer events. I missed the social events. I missed the hackathon. I only went to one day. And I now see that it would have been far better for networking, for getting to know the IETF, to have gone to the entire meeting. So that's my first piece of advice. Second, I presented 2 drafts at my very first meeting. I would recommend going to an IETF meeting or participating remotely and getting a feel for how things go before starting with your first draft. I was very lucky. I had a very prolific IETF participant to sort of guide me through the process, but not everyone's going to have that. So I'd suggest attending first and then submitting drafts. So I submitted 2 drafts, like I said, first an architecture draft, and that went really well. It was welcomed, but there were some revisions needed to it. The second one was my manifest draft, and it was wholeheartedly rejected because of that ASN1 encoding that I'd been asked to switch to. And they pretty well insisted that it needed to be encoded in CBOR instead. So not only did I have a false economy of reusing parsers, but then I had to change back anyway. And there were some pretty major changes that were wanted. So the IETF really dramatically shaped my work. Rigor is so important in the IETF. And it's interesting because this wasn't drawn out by people demanding rigor. Instead, it was drawn out by discussions. And what I found was that as I was drafting this manifest, and as I was talking to people on the IETF mailing list, explaining the reasoning behind things, I found that I was constantly having the same conversation. And that conversation was, I don't think that we need this piece of information that you've put in the manifest. Can we take it out, please? And I kept having to say, well, no, actually, we need that. And in the end, what we ended up doing with myself and some of my colleagues was we went and wrote a threat model and a set of security requirements and usability requirements. And then we anchored every single information element we defined back to those requirements. And once we'd done that, everyone understood what we were saying. Everyone knew how we had gotten where we were. And once everyone, once we had that common grounding for this work, we were able to sort of move past this constant questioning of why everything was in there. So I found that process, being very rigorous, saying we need this because of that, that was a really useful approach, and it made me much more rigorous in my work, even outside of the IETF. And the other thing was that we ended up completely reimagining what we were trying to achieve in the firmware manifest, and going right back to the very basics. What's it for, and what's the simplest way to express that? And that was a really useful exercise. A lot of people will say about standards organizations that you end up with a design by committee, and I haven't found that the IETF is like that. What I have found is that there's a lot of viewpoints and a lot of use cases, and that's really useful for defining something that's going to be productive over the long term. And bad ideas get pointed out. And I've had a few of my ideas, which I thought were great when I first came up with them. I've had people explain to me, and they've been really kind about it. It hasn't been an aggressive thing at all. It's been just a really useful way that people have said, actually, I'm not sure this is such a great idea, and this is why. And it was really useful. It's come out to make a much better standard in the end. Well, hopefully, it's not ratified yet. And there are a few reasons that I would recommend going into the IETF. And first, there's this collaboration, and it's a really phenomenal group of people, some of the smartest people I've ever met. And there's also, from a more business perspective, it helps your organization to plan for the future. And that means, knowing what kind of protocols will be coming up in the future, what kind of document formats, and also giving your organization some influence over those protocols and document formats. And that can be really helpful if you've got a particular use case in mind that isn't really catered for by existing technologies. On top of this, there are advantages in really thorough and rigorous definitions of interfaces and protocols. When they're not rigorously defined, you'll find that subtle bugs will pop up because different people understand the protocol definitions differently. And going through the IETF standardization process really helps to iron these things out. And the thorough review leads to fewer bugs over the long term. So with that, I'll get on to my introduction to firmware updates and suit manifests. So firmware updates should be simple. You have some firmware, you need to put it on a device. This does not sound that complicated. Unfortunately, the reality is not that simple. Usually you have several different kinds of devices, and they typically take different firmwares. And that makes things much more complicated to start with. But that's not all there is to it. You frequently have different networks to deal with, and possibly different device operators, the people who manage the day-to-day operation of your devices, that show up between the firmware authors and the devices. You may have multiple firmware authors writing software for different devices. And so this ends up being really complex to define and to manage. Well, one of the common answers to this problem is, well, let's just put it in a cloud service. And that seems really simple as well. We'll just put some firmware on the cloud will figure it out and deliver it to the device that it depends on, that depends on that firmware. Well, but then we've got these operators and firmware authors, and they all have to have some kind of communication with this cloud service, and the data's got to flow through it somehow. And well, that means that everybody's trusting this cloud service. And the question is, what happens if something goes wrong? What happens if someone breaks into that cloud service? Everyone trusts it. So what happens next? Well, who do you trust? Should you trust a cloud provider, an operator, a device manufacturer, or a firmware author? This all depends on exactly what you're trying to achieve. And a one-size-fits-all solution probably isn't going to be right for everyone. So we have to anchor some trust. So booting firmware requires trust. You have to prove that it's the right firmware for the device. Installing firmware requires trust as well for the same reasons. And we get trust through authentication, which is provided through cryptographic tools, either signatures or message authentication codes. But what should we authenticate? Well, the frequent approach is that we just need to make sure that the firmware is signed. But I've found that's not actually enough. You also need to know which devices should be using the firmware, how it's packed, where to put it, how to get it. So we really just need to authenticate anything that's important to the device. So really what we need is metadata that allows a device to answer all of its fundamental questions. Does it trust the author of the update? Has the update been corrupted? Does it apply to this particular device or class of devices? Is it older than the current firmware? Because that might allow an attacker to use an old firmware with a known vulnerability to take over your device. When should the device apply the update? If you don't have the ability to coordinate updates between devices, then devices that communicate with each other could potentially wind up being incompatible at a critical moment. How should devices apply updates? If you have a packed update, a differential update, for instance, then you need to know how to apply it and what its precursor is. What kind of update is it? Is it code? Is it data? And where should it be obtained from? Where should it be stored? So that's the introduction. Now the question is, how do we design a format to fit this? Well, we have a few design goals. The first thing we want to avoid is confusing users. So to do that, we need to make sure that there's very few different tools for accomplishing similar jobs. So that means that you don't want a lot of subtly different formats with subtly different tools. If you've got 7 different devices that take 7 different manifests, then there's a strong chance that somebody's going to attempt to make an update for one device that really should have a format A, but it gets built with format B and then nothing works. Similarly, you don't want a lot of different subtly similar versions of formats. And you need a way for devices to tell management systems and operators exactly what they can do and what kind of manifest they need. You also want to keep the parser very simple, and the parser needs to be simple to enable low-end use cases. So if you have very constrained devices, then we can't be spending hundreds of kilobytes in handling the parsing. To do that, we need to prioritize regular structures. So structures that aren't deeply nested, things that are simple for a parser to traverse, and flat encodings. Deep nesting causes similar problems. We also want to make sure that there aren't a lot of information elements that are mutually incompatible. So you don't want a device to be choosing from among multiple providers of a firmware image, but also needing to choose between 2 different firmware images without having fully thought through what that looks like when it has to make those 2 different choices. Then there's the need for fine-grained access control. So this means that if you have a device that supports multiple firmware images, where one firmware image, for example, contains configuration data and another contains the actual code that gets executed, then there needs to be a way to say who's allowed to write to each of those spots. We also need enough flexibility to accommodate a lot of use cases that we already know that people have asked for and some that we expect. So there are a couple of obvious choices. So first there's packed binary manifests. That's sort of the default. Then there's hierarchical descriptive documents. So that would be something like a encoded CBOR descriptive manifest. Both of these have some pros and cons. They're quite flexible, but they do produce some confusion about tool variants, and the parser can be quite complicated for descriptive documents. And with the packed binary manifests, it does get quite complex to define exactly what each device can do and also enable that fine-grained access control. So after quite a lot of discussion in the IETF, I had a lot of use cases and a lot of people asking for their use case to be supported. And many of these use cases were mutually exclusive. And I realized at some point that these use cases all were very similar fundamental operations, but in different orders and with different destinations and sources. And so that engagement with the IETF led me to find an alternate option. We went back to basics. What is a manifest actually for? Well, it's to tell a device about an update. And it's not really to tell the device what the update is, but it needs to tell a device what to do. It needs to know if it's authentic. It needs to know if it's the right update for the device and the most recent. It also needs to know where to get any components of that update. Now, manifests get used for other things, like communicating to other entities, like management systems, device managers, that kind of thing, about an update. And they also get used for listing version numbers and describing updates to humans. But do devices actually need those capabilities? Is that something that your end device really needs to know about? So we want something a little bit different in an alternate option. It needs to be simple to parse. That means it needs that regular structure. It needs to be simple to process. So that means it needs to match the way that a device will actually process the document so that getting the information the device needs when it needs it is straightforward. It needs to be simple to extend. If there's a feature that's missing, there needs to be a simple way to add it. There also needs to be simple capability reporting. Being able to decide exactly what each device can do and what kind of data it needs should be very straightforward, because otherwise a whole new protocol is needed. And there need to be simple access control lists that can allow a device, a low-end device, to understand what each entity that has access to that device is permitted to do. And finally, dependencies. There needs to be a way to handle dependencies between different components on the device without being overly complicated. So what if we were to describe the behavior of the device rather than the data that it receives? Well, conventional manifests do describe that data, and it's inherently hierarchical and irregular, which makes that parser much more complex. But if we define the behavior of the device instead, well, we're defining a process. It becomes a sequence of actions to perform, a recipe, if you will. And it's inherently flat because it's a list of operations and regular. It does need a little bit of hierarchical data, but not a lot. And this ends up resolving any ambiguity between different options that might exist. If you have two different mutually exclusive options, because it operates in a sequence, one will take precedence by default. There are no mutually exclusive operations. So we could use a bytecode. It's essentially instructions that run on an interpreter. And that defines the behavior of the system in an easily machine readable way. And it can be very tailored to a particular use case. So we can make an update bytecode. And that can make it really compact. Now, it's not necessarily general purpose though. Now, interpreters can be very complex or they can be very simple. So Lua, for example, is a very simple bytecode interpreter, whereas Python would probably be the wrong choice for updates specifically, MicroPython notwithstanding. So an update interpreter, we need to understand what kind of complexity an update interpreter would have. It would need to be able to understand what update does. We need to understand what list of operations the update interpreter would perform so that we can understand how complex it would be. So we can put some limitations on the interpreter and say, for example, you can only have predefined variables, and that limits some sources of complexity. And you can't have any loops. There might be a few exceptions to that. And no reverse branches, which eliminates the halting problem. So now we can be certain that we don't end up with an arbitrary complexity in a firmware update, which would be less than ideal. We could say no string operations and no arithmetic so that we're certain this is definitely not a Turing complete language. So there are a few operations that we definitely need. Setting parameters, verifying a device's identity, verifying the presence of an image, fetching an image or document, and activating that image or document. There are a lot of optional operations as well, such as checking component properties or system properties, asking for some kind of third-party authorization, processing some sub-behaviors or dependencies, or invoking an image, telling that image to run, waiting for an event, maybe to synchronize updates between multiple devices. And there's also a way to add additional operations fairly easily by adding a new bytecode. So I did implement this parser, and I built a simple use case, an AB image bootloader, and it includes all the mandatory operations and CBOR parsing. The number I have here does not include cryptographic operations or IO, but that brings it down to just shy of 2 kilobytes when compiled for Cortex-M4, and encompasses most of the logic that you'd find in a conventional bootloader. So this is a very small piece of code considering what it does. So if we look at these choices that we have again, we could use the packed binary manifests or hierarchical documents, or maybe a behavioral definition. Now, it's not the lowest complexity. It's certainly less complex to look at a packed binary manifest, but at the same time, each packed binary manifest for each different device could be subtly different, whereas this will have the same format regardless of which device it targets. And that makes the tool usage much easier. Likewise, with hierarchical documents, the parser will be much more complex. But again, we'll have this problem with ambiguity between different fields, extensions. There are lots of different problems that this can construct. So that is what we've done in Suit in the end. Behavioral updates are essentially how the model works. So let's talk through exactly how this works. So these manifests are processed in a specific order, and the order is based on some rules. The rules for update are that all dependencies need to be fetched and validated before any payload, that's dependency manifests, are fetched and validated before any payload is fetched. And in some applications, payloads need to be fetched and validated before any payload's installed. Then for trusted boot, there's a similar pair of rules. All dependencies and payloads must be validated before any image is loaded, and any loaded image must be validated before it's executed. So the result of that, because of those rules, is that we divide the manifest into 6 primary sections: dependency resolution, payload fetch, payload installation, then system validation is the first part of the boot sequence, and image loading and image invocation. Now, a lot of these sections use common information, so there's another section called common that's added, and it gets run before each of these. Now, there's some reference information that lives outside of the sequential structure of the manifest, such as the structure version of the manifest and its sequence number. And some information has to live outside of the scope of these commands to simplify the parser design, like a list of dependencies and a list of components. So how does the updater actually work? Well, the first thing it does is it selects the latest valid and supported manifest. So valid meaning that its authenticity has been verified through a signature, and latest meaning it has the highest value of sequence number. Then the next thing is to perform dependency resolution. So to do that, the parser runs the bytecodes in common and then runs the bytecodes in the dependency resolution section. Then to perform an image fetch, it's essentially the same operation. Run the bytecodes in common, then run the bytecodes in the payload fetch section. And again, the same thing with image installation. And trusted boot looks almost the same. Start with finding the latest valid supported manifest, then do common and system validation, then do common and image loading, and then do common and image invocation. So you can see that the parser runs in a very consistent way, which again simplifies the complexity of that parser. Now, parameters are interesting because they allow us to change the behavior of a manifest slightly. So there are a few particular use cases that these enable. Now, parameters are used to simplify the construction of the parser because there are some things that require parameters. They have to be set in advance. These are essentially like variables. So they can reflect configuration. Some can be overridden, and that allows some interesting use cases, such as if I download my firmware manifest from another party, such as the device's original manufacturer, but I want to host the payload that it targets on my own infrastructure so that all of my devices aren't requesting this from somewhere else and going outside of my network, then I can produce a new manifest that overrides the URI that was provided in the original manifest and then links the original manifest as a dependency. This allows the device to retarget where it's looking for an update and then get that image from my own infrastructure, but do that in a trustable way because it's signed by me and I presumably have the permissions to do that on my devices. Some parameters can be changed based on a decision. So if you have 2 slots that your device can boot from, then you can use a system property to decide which image to download or which image to boot. And access control lists can control the write access to each of these parameters. So that means that you can prevent, for example, someone who doesn't have authority to write an image digest from doing that, and only someone who does have authority to specify what an image digest should be would be allowed to write to that. And for consistency, all commands operate on parameters. So there are a few exceptions to that, but pretty much everything other than flow control, parameter setting, and components and dependencies are done with parameters rather than some kind of argument. There's a fairly short list of parameters. The most common ones are these. They allow a device to identify whether a manifest is intended for it using the 3 different IDs. The URI tells a device where to look to obtain its firmware image. Encryption, compression, and unpack info are the structures that the device uses to understand how to use a payload that it's downloaded. Source component is used to copy from one place to another on a device, which is useful for the image loading use case. It's also useful for swapping, which is a common way to handle booting devices. For example, MCU boot swaps between an active firmware image and a candidate firmware image. The image digest tells a device how to ensure that the image's integrity has been protected correctly, and the image size tells it, well, how much to copy. There are ways to extend the parameter list. Simply by adding a new parameter, a device can have new functionality added. And some application-specific parameters can be used as well, but the problem with that is that unless the tools on the intermediate system understand what those parameters are, they won't be able to interpret them. So that means that management systems, for example, will have difficulty understanding exactly what a manifest does if it doesn't understand any application-specific parameters or commands that are used. And I have a whole bunch more detail that I could go into, but I thought that it would be good to take some questions if there are any at this point. So let me get that open. Do we have any questions? No questions. Okay, well, I have some more material in that case, if we've got
Brendan,
time. Yeah.
do you have an example in your this thing that how does this look?
I do, in fact.
Oh, perfect.
So a simple, let's start with a simple update. So essentially the way this works is you have a manifest. Now this obviously isn't the encoded version. If you really want to dig into the nuts and bolts of it, I recommend looking at the RFC draft. There are lots of examples in it. But from a high level view, the way that a simple update would work is you would define a sequence number of your component, and you would use the you would define a component. Now, components can be a simple concept or they can be more complex. This allows you to, for example, express an entire file system path in your component identifier. But for a simple device, you don't need that kind of complexity, so a component can be very simple. A component identifier can be very simple. So first, the common section would define what the digest of a payload is, and then tell a device to check its vendor ID and class ID. Next, it would run the image installation section, which would specify a parameter, and then do a copy. So it would download that the payload at that parameter. Now, since there's only one component, it already knows that that's the only component it can be using. And so that file will be downloaded to that component location. Next, a check image hash tells the device to verify that it's got the right digest, which means that the file hasn't been corrupted or tampered with. And then finally, it can do an activate. Now, the activate tells it that this is a good image and that the bootloader can now use it. I see there's a question.
Hello, are you able to?
Yes, I can hear.
Yeah, so I have one question that that building the trust between the devices and the operator and like this, right? Why not any trust model be used instead of simple means the encryption or for authentication? Is
So
there
I'm sorry, I don't understand what you mean by a trust model.
the trust model means something like based on some the calculation of trust factor, that is it valid or the operator is valid or not, like this.
Okay, so typically the way that we recommend doing this is to so there's a whole variety of factors that play into this. So the first thing is that we're assuming that a device already has a trust anchor in it, and that trust anchor is presumed to be some kind of public key, or possibly a pre-shared key. That can be extended in a variety of ways. For example, the current version of the manifest draft specifies a delegation chain as one of the things that you can do. And that's a sequence of CBOR web tokens that each contain a key claim. Now, the idea there is that the first one that the device comes across should be authenticated by its trust anchor, and then it can iterate through this chain until it arrives at the last one, verifying each key claim in turn, and then taking that particular key as the trusted key until it gets to the one that has signed the manifest, at which point it can verify the manifest. Does that answer your question?
Yeah, thanks.
Okay. I've got a component update example as well. So this one shows that there are two different components that can be used. And so again, there's this process of checking vendor IDs and class IDs, but now things are a little bit more complicated because the device has to know which component it's operating on. So the first thing to do is specify that it's component index 0, so that's the first component in the component array. and then it sets the digest, then it switches to the second component and again sets the digest. Then when we get to image installation, again, we have to do the same thing. We set the component index to 0 and then specify the URI, set the component index to 1 and then specify the URI. Now there's a slight optimization available in the manifest, which is that when the component index is set to true, it means all components. And so then doing the download happens for every component in turn. And then finally checking the image hash, again, does it for every component in turn. And then the device finally activates the components it has. So there's quite a lot of flexibility built into this. And the encoding is also very small. The manifests built this way, excluding the signature size, tend to be under 100 bytes quite regularly, sometimes as high as 200, but generally it's a very small way of encoding the update process. And the advantage that this has is that it can manage very complex use cases without overly increasing the complexity of the parser or of the device. Because the actual decisions that need to be made and the sequence of operations is all encoded into the manifest itself, this means that the device can simply do the individual operations it's been instructed to without introducing any additional complexity on the device. As an example of that, here's a way to do an A/B image selection. So the idea here is that I have two bootable locations on my device, and they need to be linked at two different offsets. Because of that, there are two different images that I could possibly need to download. And the way that I handle this is I have a way of running a conditional sequence. So I can check whether the current offset for downloading is the offset of slot A or the offset of slot B, and then set the digest accordingly. And likewise, when it comes to downloading the firmware, I can again check which offset I'm at and set the URI accordingly so that I pick the correct image to download from my device. And this allows a single manifest to describe both possible updates, both possible URIs, without the operator of those devices needing to know which slot each device is running from, which greatly simplifies things. Dependencies are substantially more complicated, and unless there's a great desire to go into those today, I think I'll skip over them. But that is roughly what they look like. You have to provide the digest of your dependency, and then you have to instruct your, in each manifest that has a dependency, you have to tell it when to process that dependency. Is there anything else that's interesting here? Yes, I'll do something. I'll talk about capability reporting unless any more questions have come in.
Hey, Brendan, you have
Yes.
2 more minutes.
2 more minutes. Okay. Well, in that case, if there are any burning questions, we can go through that. And if not, then maybe I'll just close it there and say I hope to hear from you on the mailing list, and I really encourage you to consider participating in the IETF. If you have an interest in IoT firmware update, please feel free to reach out to me. You can easily find my email address if it's not in this. It's definitely in the suit manifest draft and the suit architecture draft, so I should be fairly easy to find. Yeah, I hope that this has been informative, and I look forward to talking to you soon.
Thank you, Brendan. Any questions? Last 1 minute we have. Otherwise, we'll move to the next.
Yeah, hi Brendan. One question from my end. So, in cases where the firmware image gets corrupted while downloading, what is the most effective counter mechanism as per the IETF standards?
Oh, in current IETF standards. Well, so the first thing is if you're using a TLS link, then the chances of it being corrupted during download are quite small, immeasurably small. So I wouldn't worry about that if you're using TLS. Now, one of the design goals of the manifest was to avoid the reliance on mechanisms like TLS because they make it much more difficult to minimize your network bandwidth. So having the capacity for multicast distribution or even local caching was a key design point. And that would also enable full broadcast, like satellite type distribution for devices. So under those circumstances, it's more complex. There are some options available. There's been a few research papers on that. I mean, the firmware update manifest doesn't actually care about this. So you could use BitTorrent if you wanted to, and that would sort you right out, if you see what I mean. But that's not necessarily the right option. So there's a lot of different ways to handle this. And I'm not certain whether there's an IETF specification that's ideally suited to that. The goal in suit was to start with handling the manifest format itself without designing a protocol as well. Now, if there's a demand for protocols to answer these questions, then that's something we can definitely look at. But the idea was that we've already got CoAP, we've already got TLS, we've already got HTTP. There's broadcast mechanisms and multicast mechanisms in a lot of these things. So we're going to ensure integrity with a digest and offer the ability to encrypt for privacy, but use at-rest encryption, and then leave the rest up to implementers, unless there's a demand for something more targeted.
Thank you.
Thanks, Brendan. So Praneeth, maybe you can introduce the next speaker.
Next, we have Thiru, who is a principal engineer at McAfee. He has expertise in network and IoT endpoint security, architecture, and developing security products and solutions. He has a proven track record of developing security and privacy standards for the internet. He is currently chairing the TEP working group and is also a member of the security area review team at the IETF. He has co-authored 22 RFCs and is an active contributor in several working groups. Thiru has 47 patents approved and 50 patents filed in USPTO. His recent work and interest include IoT security, service function chaining, DDoS mitigation, and encrypted DNS. So today, Thiru would be explaining to us the manufacturer usage description TLS profiles for IoT. Without further ado, I would like to welcome Thiru and kick this off. Hi, Thiru. Please take over.
Hey, thanks, Praneeth, for the introduction. Let me share the slides. Give me a second. Okay.
Yes, they are visible.
Okay, great. Okay. Hey, that was a great presentation from Brendan, and I would continue that. I mean, this is probably a different tangent than what Brendan has presented. So I'll this draft was recently adapted by the working group a couple of months back after several discussions in both OPS, WG, and TLS working groups. Before I jump into this draft, right? I mean, I would just like to talk about what's happening in the IoT world, right? I mean, I know today we all know that IoT is used in every segment, right? It's used in home networks, enterprise networks, your industrial IoT. It's used in hospitals for controlling your nuclear reactors. It's used in various places, right? I mean, and especially in the consumer segment and enterprise segment, right? I mean, there's been an explosion of IoT devices, right? I mean, if you just talk about the IoT devices that we have in our home itself, right? I mean, there's so many sophisticated smart cameras, smart speakers, smart locks, and they're quite expensive devices. And in addition to the expense, right, they're as good as any mobile or a laptop device. And the bigger impact is that if these devices do get compromised, it's not only going to infect the device and invade the privacy, but also it will result in a privacy and a security threat for a physical threat to the user of the devices. For example, if my smart lock is hacked, it could just lock me out or lock me in and doesn't let me to get out or get in. an IoT device which is administered for, let's say, your pacing, heart pacing could not function properly. Your smartwatch could be sending the details of all the activity that you are doing to an attacker. Recently, we have seen an interesting IoT attack where the attacker, after infecting the device with a malware, would use it for his own purpose and then convert the IoT device into a brick. That means the IoT device becomes no longer usable, right? I mean, those threats are quite different than the threats that we typically see on a laptop or a mobile device, because they could be life-threatening threats, and the impact of these threats are far more damaging than what would typically see if my laptop or a mobile device gets hacked, right? And And if you see, there's several discussions happening at IETF in various forms with regard to security, that unfortunately, many of these IoT devices, which are probably purchased off the shelf, are not don't are built without security in mind, which causes them to have several vulnerabilities, and it's easily exploited by malware to infect these devices and use these devices for attacking the homeowner or the user of these devices, or launch DDoS attacks on a public server, so that they use these servers as their agents for, let's say, launching a DDoS attack on a public server, like a banking site, right? And that's the sophistication of these IoT devices, that we've seen various levels of attacks that's being used both on the user of the IoT device. For example, it could be stealing your video streaming information from the IoT device. It could be, for example, infected in a way that it could be used for crypto mining to earn bitcoins. There's several such attacks that we've seen increasing in the last few years, and in the last few months, especially after the COVID effect, we have seen almost as significant increase in the number of attacks that we are seeing on IoT devices, and the rate of these attacks has been increasing dramatically. Uh, One of the interesting trends that we see, right? I mean, if you see, IETF has been pushing that in the right way, that all the protocols should move towards using TLS or DTLS, get to have peer-to-peer authentication, and have the right cipher suits for encryption. And malware authors have also started realizing that, hey, it's good for them to even move to TLS, because it makes it quite difficult for a middle box or a firewall to identify malwares. And if you see the recent malware trend, the new malwares that we see in our labs, they're all written using SSL or TLS. And nowadays, I would say that more than 70% of the malware is using encryption to avoid detection by middle boxes. And they try to, and it's not just about malwares being sophisticated in their communication. They also try to leverage the vulnerabilities of operating systems. For example, recently there was a cryptographic vulnerability in Windows, where it failed to validate the server certificate, and that was leveraged by malware to infect the operating system with malware. So the trend of IoT malware has started growing beyond what we used to see with endpoint devices like mobile phones. There was a plethora of malwares that were there, but now we see a drastic increase in the malwares that we see with IoT devices. Right. And what has ITF been doing with regard to protecting IoT devices? Right. I know there's several working groups at ITF which work on IoT, and manufacturer usage description was something that was standardized, I think, a couple of years back. There's several implementations of that available. So what it does basically is, if you take any IoT device, a simple IoT device like a light bulb, it has a specific purpose, right? I mean, it goes to specific set of domains, beyond which it does not go to any other domain, because its only purpose is to turn or turn off the light or change the colors of the light. So for these devices, it was quite easily identified that you could create a manufacturer usage description file which would tell what this device is supposed to do. For example, it's supposed to visit XYZ domains, it's supposed to talk to another IoT device within the home, or it's not supposed to talk to any other IoT device in the home. So that basic whitelist rules was that could be created with MUD, and that's what the would be advertised and learned by the network device within the enterprise or home network, and that would start enforcing the policy. So it becomes quite easy for a middle box to know that, hey, this device is supposed to only go to this domain, so that creates a whitelist for me, and anything else is a blacklist, so all other traffic it gets dropped or blocked. Now that solved problem for several of the IoT devices that are there, which have simple functions like light bulbs, uh, which we would typically call as headless IoT devices, because they don't have any special skills that you would start teaching them. But then the problem comes with the advanced type of IoT devices, which could be your voice assistants like Amazon Echo or Google Home, or your streaming devices like Comcast, Fire TV, and they have broad range of communication patterns. They, based on the skills that you train them, they may start talking to newer domains. They may want to talk to other devices within the home, and then the problem comes is that you cannot have a static MUD file, because that would be specific to each device that you have in your home or enterprise network, and the rules will be quite different and cannot be programmed into the MUD file that can be pushed onto the firewall to enforce those policies. Um, with that trend happening, I mean, the rules that you see in this MUD file that you see in RFC 850 are simple ACL rules based on your IP address, port numbers, TCP, UDP. It was extended to add domain names, because that made it quite easy to whitelist and blacklist domain names. But now that we see that encrypted DNS has come in the last couple of years, either with regard to DNS over TLS or DNS over HTTPS, now we see that malwares have started using encrypted DNS. So the middle box would not even see the DNS traffic to, first of all, identify whether the client is actually visiting domains it is supposed to visit or not. And then we have seen a growing trend where malware have started using privacy enhancing tools like Tor. And if you're using privacy enhancing tools like Tor, as many of may be aware that Tor does not use DNS at all, and you reach the Tor malware could reach to a command and control server hosted in the Onion in the Tor network. Uh, and that was creating quite a challenge for us to see that how do you protect these devices which have broad communication patterns, and they have a very they have a dollar value attached to that, and have a far damaging impact on the user who is trying to use them. And because they have a lot of compute power, they could be used for attacking any public server, or it could be used for Bitcoin mining. So there's so many such attacks that we were seeing, and some of these attacks may or may not damage the user who is using those devices. But in overall, if there is a malware, the malware author could do anything, program the IoT device to do anything for monetary benefits. And now, with that intent, we were looking at ways for identifying and protecting these IoT devices. And as many of you may know that in several endpoints do have endpoint host agents like AVs, endpoint security agents that could run on mobile devices, but you don't have anything that like that available on IoT devices. Now, what could we do to solve that problem, right? So we've been working on protecting IoT devices both in enterprise and home networks for quite some time. And we were looking at trying to see that if MUD could be extended with regard to the TLS interactions that it does, because TLS has become the de facto protocol for both the good guys and the bad guys to use it for legitimate purposes, and even to use it for for malified instances where the malware wants to use it and to get command and control instructions, or to send leak data from your network, or steal data from the IoT device. So there's several such attacks, and most of this communication is happening through TLS. When I refer to TLS, it refers to both TLS and DTLS, and CoAP runs over both TLS and DTLS, and DTLS is quite popular because of its characteristics than TLS. Uh, Now, when we analyze the malware flows to legitimate flows, we observed that the malware flows had several characteristics which were quite different from legitimate flows. For example, if you see in this example that I have here, uh, the malware actually would say that it wants to reach example.com, but in the certificate it would be example.net. For example, it could be a better example would be to say the SNI would say it wants to reach youtube.com, but the certificate would have actually the certificate of the command and control server, which is probably a domain generated algorithm. And that's how they want to basically fool any middle box which is just looking at SNI, and SNI shows it's going to YouTube, and it would say it's a good traffic, but the certificate would be actually of the command and control server. Uh, there's several such differences that we saw with regard to the way they were using DGA, because if you look at this example, it's not a typical domain name that we'd see. It was generated by a machine, and that's what the malware was using. There were several other parameters, like the cipher suits that the malware would use was quite different from the cipher suits that we would see an IoT device was using. The supported groups, TLS extensions, various other TLS parameters that you see in a TLS profile were quite different for a legitimate software versus what we saw in a malware. And we've seen several malwares which were using self-signed certificates, and that was probably because they didn't want to go to a public CA and get an certificate signed, and the probably the malware authors thought that self-signed certificate is what is the best way, and they have pinned that certificate in the malware running on the IoT devices. And the most interesting one was these malwares are never compliant with what we define at IETF. For example, IETF has best practices for TLS 1.2, which is defined in RFC 7525. It talks about what software suite should not be used, expired certificates, several such best practices which are being discussed and used by legitimate software is never used by malwares. I've never seen a malware flow which is compliant and using the best and the right way of using TLS that is recommended for legitimate software. I could just talk about and more of the attacks, but for instance, if you see here, recently there was an attack with Asus home router, and it failed to validate the certificate, because of which any malware could send any bogus firmware update, and that would be installed on the Asus home router, and that becomes a launch pad to basically infect your home network devices, or it could be changing your DNS setting, and various such attacks started revealing with the inability of these IoT devices to validate certificates. And Samsung was a very classic example, that the Samsung fridge, which was quite an expensive fridge, failed to validate server certificate, and that caused a lot of damage. And Samsung came out and fixed that eventually. But you can see the level of, imagine if these vendors have these kind of problems, imagine the devices coming off the shelf and the kind of vulnerabilities they have. And unfortunately, the end user is not even aware of what kind of vulnerabilities are there on these IoT devices. Uh, that probably sets the context of the problem that we are trying to solve. So to address that problem, what we are trying to do in mud TLS profiles is for the IoT device to declare the TLS profiles it uses. So what we have learned is that since an IoT device is a constrained device, it has a fixed set of TLS profiles that would not change even after you learn a new skill, even if it has a broad communication pattern. And it also helps the middle box like firewall to know whether the IoT device is a compliant IoT device, whether it is using the right cipher suits, whether it is using the right TLS versions, whether it is using any self-signed certificates. So that way, the middle box is far more aware of uh, what kind of SSL stack that the IoT device is using, rather than just going through and inspecting all the traffic from the IoT device based on signatures to figure out whether it's a good or a bad traffic. So with that, I mean, before even we publish this draft, right? I mean, McAfee offers both home network security and enterprise security, and we've been profiling IoT devices in our lab and in collecting telemetry data. And we observed the TLS profile from several of these IoT devices, and we noticed that these profiles did not change even after learning new skills, and which was a good point. And what we realized is that each of these devices had different DTLS profiles. So Amazon Echo itself had a different DTLS profile than what you would find in Google Home, and it would be completely different from what Kindle was using. And the best part was the malware flows had TLS profile parameters, which was quite different than what we saw was used by legitimate flows coming from these IoT devices. Um, so what we did was I published a draft probably an year and a half back, uh, uh, explaining to the working group how if the IoT devices manufacturer starts publishing the TLS profile back to the network devices, so that they can enforce policies that would solve these attacks that would be there. It's a Yang model. We are extending the ACL Yang model to discuss the TLS profiles. I'm not going to go over all the parameters. I'm just going to talk about a couple of them. For example, here we talk about the cipher suits that are used by the IoT device, the TLS versions it supports, the CS that uses, because we see that each IoT device may have a different trust anchor. So the trust anchors that it may have could differ from IoT device to IoT device. So that gives a valuable information for the middle box to know what kind of trust anchors are used by the IoT device. So several such parameters that we had identified, which would help us identify what is the right TLS profile, and if there is any deviation from that, that would help us to identify and block malware. Uh, uh, I mean, this is some of the captures that we got from our lab for demonstration purposes. So if you see, this is traffic from Google Home, and we have these malware samples collected from our sandboxing environment in our threat defense lab. And this malware samples is from thousands of malwares that we had sandboxed and generated traffic. If you see, this is just cipher suits. There's a big difference between there is some overlap in some places, but you will see that there's a lot of differences in the way that cipher suits are used by malware versus what is used by Google Home. Um, Several other parameters. If you see, malware has been using empty SSL version. It was using TLS 1.0. Google Home legitimate flows were using TLS 1.3, and we never saw a malware which was using TLS 1.3. There were some good and bad flows which are using TLS 1.2. Right, and it's very similar, right? If you look at each of these parameters, they were quite, we could see several distinguishing factors, and if you combine all of that, we could realize that we had enough information to block most of the malware successfully. For example, the extension types, what we saw was malware was using encrypt and MAC, which none of the legitimate flows were using. They were using heartbeat extension, which was not used by any of the legitimate flows. The supported groups were quite different from malware to legitimate flows. Uh, uh, Google Home never used any self-sign certificates, but we saw that malware was using self-sign certificates. So with that information, what we realized that if you could extend the ACL and MUD to have TLS profile parameters, that then it would help us solve the problem of identifying and blocking sophisticated malware to block at the TLS level. Uh, And the best part was, since each of these devices had different profiles, it becomes quite a challenge for a malware agent to start mimicking the DTLS profile of each and every IoT device type, make, and model, because all these IoT devices that we have observed have different TLS profiles. So if a malware author has to develop an IoT device type, model, and firmware version specific malware, then he has to develop like thousands of malwares, and which becomes quite impractical. And that's the reason we thought that publishing this TTLS profile is probably a way forward to solve some and detect some of the malwares that are there in the world. I'm not going to go into several malwares, so I just picked one malware just to show an example. This malware was having weird characteristics. For example, it was using self-sign certificates, it was using weak cipher, it was lying about the server that it wants to reach, probably to full middle boxes. Several of its server certificate parameters were null, and this family of malware kept evolving and changing the way it does. But there were quite few characteristics from each of these malwares that we could use and identify and block malware flows. Uh, Now, what happens when TLS 1.3 comes? So with TLS 1.3, what would happen is that other than the client hello, most of the handshake is encrypted, in which case a middle box, which is just passively inspecting the traffic, would not be able to identify what is the certificate, what type of server certificate is being sent, what kind of negotiation is happening at a TLS level, because other than the client hello, rest all parameters are blocked. Even for middle boxes where they cannot act as a TLS proxy, we observed that even by just looking at the client hello parameters, we could identify a good percentage of malwares. For example, we saw malwares which were using evasion techniques like randomizing the client hello parameters for every TLS handshake, and that could be easily detected and blocked, even if the malware, even if the middle box doesn't do a TLS proxy implementation. But with TLS 1.3, because most of these parameters are hidden, the only way forward is if you have a middle box which can act as a TLS proxy, then it can use these TLS profiles to identify what is the right set of profile and block any malicious profile. Now, many people keep asking us that, hey, you're acting as a middle box and you're inspecting traffic. But if you look into the discussions that we had when TLS 1.3 became a standard, was there are ways that you can be an compliant TLS proxy, and that's what is discussed in the TLS 1.3 spec. So there's various discussions that we had in TLS 1.3 working group, which talks about what does it mean to have a compliant TLS proxy that will not impede the protocol enhancements that happen at TLS 1.3, and at the same time, this proxy does not have impact the endpoint in any way that it would result in a security degradation on the endpoint. And TLS proxy, as we all know, is only possible in networks where you have IT managed IoT devices, where you could install your enterprise root certificates. And the advantage of this mechanism, what we realized is that you could just inspect the traffic at the TLS handshake level because you are acting as a DTLS proxy, but then you can skip all the payload. You don't even have to look into the payload. And with the way we had defined these profiles was, if the IoT device is talking to specific destinations which are well known, then in those cases, the firewall does not even have to start acting on the traffic, and it can simply bypass. So that way, with this profile, what would happen is that certain flows, certain suspicious flows would be subjected to TLS 1.3 inspection, and this TLS profile would come in handy for the middle boxes to identify and block malicious flows. Any questions, comments?
Any questions, folks? You can use the Q&A, or if anybody would like to speak, you can also send me a message. I will enable your mic. Please ask questions. Brendan, did you wanted to ask a question? Brendan, we can't hear you if you are trying to speak.
How about now?
Yes, go ahead.
Yes,
Okay,
we can
brilliant.
hear you.
Okay, so I have a question about setting up the DNS URLs for MUD DNS rules.
Mhm.
I'd like to know how you would handle, for example, a DNS server that returns bad results. So if I were a malware author and I set up a DNS that gave a command and control server as a response to any query, then I could request a DNS result from that server, and it would always give me my CNC server.
Sure.
So how does MUD address that?
So MUD addresses that in a way that it would say which DNS servers you're supposed to use.
Okay, and
right,
then
with
the
an
second
ACL.
question.
Yeah,
Okay, no,
and
that makes sense.
Okay.
The second question I've got is, how do you handle DOT and DOH?
So yeah, that's a good question. So DOT DOH, as you know, has been standardized in both deprive and DOH working groups. Unfortunately, till now, we don't have discovery mechanisms for DOH and DOT. What we see today with Firefox, Chrome, or Windows is that they support some public servers. So if you are attached to a network, let's say 8.8.8 is the DNS server that it sees, then it would auto upgrade to use a DOH connection. There is no mechanism that is available on an IoT device or an endpoint to discover the network provided DOH or DOT resolvers. And that's what recently a working group called AD was formed. It's for adaptive DNS discovery, where several of these enterprise guys, home security guys, and ISPs came forward saying they can also offer DOH servers and DOT servers, and they would want a mechanism where the endpoint can start discovering that and using that. So once that discovery mechanism comes in place, the IoT device would in fact discover the DOH DOT server hosted by my local home network or my ISP or my enterprise network, and that way the same device would both resolve your queries and enforce these filtering rules.
Okay, so until such a time as we have local DOT or DOH capability, then the only option for IoT devices is to prohibit the use of DOT and DOH. Is that correct?
Uh, I have not seen any IoT device till date which is using DOH DOT. So
Okay,
yeah,
right.
but
I'm just
yeah,
sorry.
but
I'm just trying to.
I think that what is happening today is every browser and every operating system has implemented DOH stack. They're just waiting for the discovery mechanism to become a standard. So I would say that having that inbuilt where you develop the DOH, I think you need a lightweight DOH stack or a lightweight DOT stack on the IoT. That itself is something that you should start. And I'm pretty sure within 6 to 1 year, we would have some discovery mechanism which would enable these IoT devices to discover the local DOH DOT servers.
Okay, thank you.
Thiru, we have one question in Q&A.
Okay, let me just see.
And I hope the Q&A is visible to everyone. Yeah, it is.
Yeah.
Perfect.
That's a good question. Yeah. Imagine there is an state-sponsored malware, right, where there's sort of sophistication, and they want to really go and really mimic what is happening on the IoT device. The middle box needs to have other mechanisms like anomaly detection and other techniques, which is what we do today to look into those kind of anomalous behaviors and ML models that we could build. So we are working on several ML models to detect any such sophisticated zero-day or state-sponsored malware which could try to bypass what we are doing here.
Thanks, Thiru. I
Okay,
think we can continue with the presentation.
I'm done, Dhruv.
Folks, any last thoughts?
So for
Any
guys who
last
are
thoughts?
interested in treeless profiles, right, just to add right through, there's a lot of research that's been happening in the industry for last 5 years. I used to work for Cisco before this, and Cisco had started a project called encrypted traffic analysis, which is now shipped in several enterprise products, not just Cisco, but it was quite interesting that that project gave light to the way that traffic how malware could be detected by looking at the TLS characteristics, and that helped in several use cases that we could start detecting malware, and that actually paved work for this. In fact, one of my co-authors is Blake Anderson from Cisco, and he's helping me with this draft. And there's a lot of research these guys have done with regard to how TLS is being used by malware, and how these profiles can help detect and block malware. So there's a lot of interesting articles and research papers on TLS profiles for malware devices.
Thiru, if there is any material that you want to link, just send me those links. I'll put them in the blogs as well as future reading, the things that you were just mentioning. So that could also be very useful for people.
Sure, sure. In fact, they're all discussed in the, some of them are discussed in the draft itself. I can add the links to
Perfect.
this
Yeah,
PPT and update and send you. Yeah.
perfect. So folks, any questions? Otherwise, we are finishing right on time. That's good. Okay. So thank you, everyone. Thanks for being here. Please feel free to use all the channels. If you have any questions, if you need some help related to attending ITF 109, we are here to help you. And I hope to see more people at ITF 109. It's on an India friendly time. Pick a few sessions that you are interested in, attend, don't be shy. And if any help is needed, feel free to ask. Thanks. Hope you have an excellent weekend. Thanks to our speakers. Thank you, Praneeth. Thanks, everyone. Take care.
Thank you.
Thank you.
Bye bye.